So, have you ever wondered why it takes days or sometimes even weeks to train one of these huge AI models? Well, the answer is kind of buried in this really fascinating math problem. Today, we're going to dive into the quest to make AI learn faster by trying to solve a method that is, in theory, absolutely perfect, but in practice, completely impossible. Let's get into it.
First, we're going to look at the standard way we train AI, which is kind of like a slow, downhill grind. Then, we'll explore a much smarter, theoretically perfect way to do it right before we smash into the billion-parameter wall that makes it impossible. But then we get to the really cool part. We'll look at two brilliant hacks, KFAC and the so-called lazy Hessian, that get us so much closer to that perfect speed.
All right, let's set the stage here. Training an AI model is really just a giant optimization problem. You're trying to find the one single lowest point in this massive, incredibly complex landscape of possible answers. But, the way we usually do it has some pretty serious limits. Yeah, this is the core question, isn't it? When you hear about these giant models training for weeks on end across thousands of GPUs, it's because the basic process they're using is this incredibly slow, step-by-step grind to the bottom. So the most common method is something called gradient descent. And honestly, the best way to picture it is to imagine you're a hiker. You're trying to get to the absolute bottom of a huge valley, but the entire valley is filled with a super dense fog. The only thing you can do is feel the ground right at your feet to figure out which way is downhill, and then you take one small step in that direction. That's it. That's basically what gradient descent is doing, just following the immediate local slope. Now, the real trouble starts when that landscape isn't just a simple round bowl. In AI, these landscapes often have these super long, narrow, winding valleys. So our hiker, who's stuck in the fog, they just end up zigzagging back and forth between the steep walls, making these tiny, tiny bits of progress down the valley floor. This problem has a name. It's called ill conditioning, and it makes the whole process just agonizingly slow. But what if our hiker wasn't stuck in the fog? What if, instead, they had a full-blown topographical map of the entire area? Well, that would be a much, much smarter way down, right?
So the smarter way is a real thing. It's called Newton's method. Instead of just knowing which way is downhill, it also understands how the slope is changing in every direction. It can see the whole curve of the valley, which lets it just aim directly for the bottom instead of taking all those tiny little zigzagging steps.
And the mathematical tool that gives us this incredible map? It's called the Hessian matrix. The Hessian is our topographical map. It's this giant grid of numbers that perfectly describes the complete shape of the landscape right where you are, every little peak, every curve. With the Hessian, you are no longer hiking blind. And this really lays out the difference perfectly. On the left, you've got gradient descent, a first-order method. It only sees the immediate slope. On the right, Newton's method is second order. It sees the slope and the curvature. It's the difference between fumbling around in a thick fog and making one single calculated jump straight to where you want to go. Okay, so if Newton's method is so amazing, why on earth don't we just use it all the time? Well, this, my friends, is where we slam right into the billion-parameter wall. Modern AI models are just gigantic. We're talking a billion parameters, sometimes way more. And every single one of those parameters is another dimension in our optimization landscape. So that topographical map we were talking about, it doesn't just need to cover a valley. It needs to map out a billion-dimensional space. Now here's the real kicker. To actually use that map to figure out our perfect jump, we have to do a mathematical operation on it called inversion. And for a matrix that's describing a billion parameters, well, it's not just slow. It's fundamentally, computationally impossible with the computers we have today. This quote from the University of Toronto just nails it. The cost to do this grows with the number of parameters cubed. That's O of d cubed. For a billion parameters, the number of calculations is, well, it's just astronomical. It would be like trying to print out and read a map the size of an entire continent just to figure out where to take your next step. It's just completely out of the question. So the perfect solution is impossible. What do? We get clever. We find a workaround. And this brings us to our very first hack for approximating that perfect map, something called KFAC. The method is called KFAC. It stands for Kronecker Factored Approximate Curvature. It's a mouthful, I know, but the idea is based on a really cool math tool called the Kronecker product. Think of it like a clever way to build a huge, really complex pattern by just repeating a much smaller, simpler pattern over and over. This lets KFAC create a simplified, much more manageable version of that impossibly huge Hessian map. To really appreciate this hack, you first have to see the true problem. This is basically what the calculations inside a real neural network look like. It's a giant tangled web. Every part is connected to and influences every other part. And this crazy interconnectedness is exactly what makes that true Hessian map so massive and so complex to figure out. And here is the genius of the K-FACT solution. It makes one big, bold, simplifying assumption. It just says, you know what? What if we just pretend that all these layers are statistically independent? By mathematically snipping those connections, that one giant, impossible Hessian matrix breaks apart into a bunch of smaller, independent blocks that are way, way easier to work with. Sure, it's not a perfect map anymore, but it turns out to be a remarkably good one that's also computationally cheap.
K-FACT is one awesome way to hack the problem. But there's another idea, and it's almost beautifully simple. It asks a different kind of question. What if we just get a little lazy?
And this is the lazy Hessian method. The logic is just so simple. The really, really expensive part of all this is calculating that full Hessian map, right? So let's just do it once. And then we reuse that same slightly out-of-date map for many, many steps. We still figure out the simple downhill direction, the gradient, at every single step, but we use our old map to help us interpret it and take a much smarter jump.
And what is just amazing is how well this works. Research has shown that by being lazy, you can actually improve the total computational cost by a factor of the square root of d, where d is the number of parameters. So for a model with 1,000,000 parameters, that's a potential 1,000-fold improvement. It turns out the best strategy is often to update that big expensive map only once for every 1,000,000 or so steps you take.
Okay, so we've seen the slow grind, we've seen the impossible ideal, and we've seen two really clever hacks that bridge that gap. So let's put it all together.
And this table right here is really the key takeaway. Gradient descent is cheap, but it's slow. Newton's method is super fast in theory, but it's computationally impossible in practice. The real breakthroughs, K-FACT and the lazy Hessian, they find that perfect sweet spot. They give us all the power of that second-order curvature information, but without the crippling cost, either by approximating the map or by cleverly reusing an old one.
So, at the end of the day, the real story here is that progress in training these massive AI models isn't about finding one single, pure, mathematically perfect algorithm. It's really a story of brilliant engineering and clever compromises. It's about finding the hacks that are good enough to unlock these incredible speed-ups in the real world.
This whole journey has been about bending the rules of a perfect method just to make it practical. And it kind of leaves us with this really fascinating question. As we build even bigger, even more complex AI, what other fundamental mathematical rules are we ready to bend next?